Okay, so let's start by recalling the theorem that we proved in the previous video. We need this recollection for today's discussion. So this is how our things started. Let V be a finite dimensional vector space over some field F, and let T be a linear operator on V whose minimal polynomial over F is P of x, and of course P of x is an element in this polynomial ring. Then what did we do? We recognized the fact that since Px is the minimal polynomial for T, so it is neither 0 nor a unit in this ring, and this ring being a Euclidean ring is a unique factorization domain. So such an element in such a ring has a factorization as a product of powers of irreducible elements. So that's how we got a factorization of Px. Then Px can be factorized like this. Lk, where these Qi's are elements in Fx and they are irreducible. And the Li's are positive integers, natural numbers. Okay. And then we considered some subsets of V. Consider for all these i's Vi. What was Vi? Vi is the set of those vectors V in V which get annihilated by the operator Qi of t to the power Li, and being annihilated means when you apply that operator on the vector you get the zero vector. What did we uncover about these subsets Vi? Then each Vi is a subspace of V invariant under T. This is what we first discovered about these subsets Vi, and that led us to have some operators on Vi themselves. Namely, if you restrict T on Vi due to this invariance, that restriction again maps Vi into Vi, and that's how we get an operator on Vi, which we called Ti. Let, and this is how we in fact wrote, let T induce the operator Ti on Vi. Again, I am repeating that this is possible only because each Vi is invariant under T. Otherwise, you may not have an operator that maps Vi into V. It may map something out, it may lead you to have some output outside Vi also. Okay, but that's not the case here. So we get operators this, and only after having these things do we see the statement of that theorem. So let's now see what the theorem says. I mean, we of course already know, so let's just recall. So the theorem was 661. In the context of all these things, this is what the theorem states. We have V as a direct sum of those VI's. That's the first thing it states. Also, the minimal polynomial of Ti for each I is that ith factor in that factorization of Px, that is this. Okay, so this is where we are now, right now. Now, this entire thing is very general in the sense that T is just any linear operator on V. We have not imposed any restriction on T whatsoever. But what will now happen if, say, all the characteristic roots of T lie within that underlying field F? In general, that's not the case. You have already come across many operators, some of whose characteristic roots don't exactly lie in the underlying field but lie in some extension of that field. But say that happens, then what can we say about this theorem? Now suppose the distinct characteristic roots, let me write it like CH roots, okay, so these are the distinct characteristic roots, all lie in F. Then we know how the factorization of the minimal polynomial Px is going to look like. It will be in terms of this characteristic roots, and it will be a very simple factorization. Then, and this is what it will be: x minus lambda 1 to the power L1, then times x minus lambda 2 to the power L2. That's how it will go. And finally, we are going to have this. So then what form will this theorem take? And we will now have a corollary based on this special situation. So let's see the corollary. So the corollary also starts like that. If the distinct characteristic roots. Oh, we did not actually say the characteristic roots of T, but that's understood. Here, however, we have to write it properly. Lambda k of T all lie in F. Then this fact of course remains the same. V is still the direct sum of those subspaces, but now the subspaces will themselves look somewhat special, where each Vi now is this. Where it's annihilated by this special operator t minus lambda I to the power Li. So that's just one part, and now what about this second part? The second part in the general theorem says what the minimal polynomial of those induced operators Ti are. So now they will also be special. Also, the minimal polynomial of Ti is, the author in fact again says what the Ti's are, but I am not repeating it because we are having the discussion. No, we know what Ti is. And the minimal polynomial is this. Okay, so this is how the corollary looks if all the characteristic roots of an operator lie in the underlying field. Now let's again go back to the general theorem and try to see what else we can get from that. And where exactly are we going with all these things? What is the end result? We are going to go towards that. Theorem 661 says this. Let me write one more subspace, V2, Vk. Now, if you recall a general result about any linear operator on V which has a decomposition like this, which we have already seen, it is about the matrix of such an operator under some special basis. We have seen this. In fact, in the beginning of all these discussions, this is what we saw. If you have a finite dimensional vector space V, which is a direct sum of some subspaces, then what you can do, and one more thing, that they are, each one of them is invariant under T, so that when you restrict the operator on any one of them, it induces an operator of that subspace, which we are calling these Ti's. Then there exists a basis of V which can be obtained by adjoining the basis for these operators, in which the matrix of T will assume a block diagonal form, where the blocks actually are the matrices of those individual Ti's in those individual bases. And the result we are talking about is lemma 651. But before we write that though, let's also let's name the dimensions of these Vi's. Let Ni be the dimension of Vi for each I. Now, by lemma 651, V has a basis in which the matrix of T, let me write there, is of the following form: A1, so these are blocks not necessarily single entries. Okay, so this block diagonal form, the matrix of T assumes where AI is an Ni by Ni matrix, where Ni is the dimension of Vi. And in fact, AI is the matrix of that induced operator Ti. In which basis? If you take the basis of V, in which the matrix of T has this form, and cut out that part of the basis which corresponds to Vi, you know what I mean, what I am trying to say, then that single portion will itself be a basis of what? Vi. And in that basis, the matrix of Ti will be that AI, which lies here somewhere. Okay. Now, what are we going to do with this information? The ultimate aim is this. The ultimate aim, of course, is this. See, if you have a vector space and on that you have a linear operator, what is it that you want to know about the operator? Its eigenvalues, characteristic roots and characteristic vectors. Now, this in general may be a very difficult task. To simplify this, what we instead seek is this. We seek an element in the similarity class of T. We already know that if you look at the operator algebra, which we are calling AFV, there you have operators, say T1, T2, many operators are there. Some of them are similar to one another. And the good thing about those operators is that they have exactly the same eigenvalues and eigenvectors. And this is an equivalence relation, two operators being similar. Let's also recall what that was. T1 and T2 are said to be similar if there exists an invertible operator S on V such that T1 is equal to this. This was the similarity relation. And this is an equivalence relation, and this relation partitions this entire operator algebra into equivalence classes. Within each class, each compartment, of course, any two operators are equivalent to each other. So if you pick any one operator, say T, say this is T, and this is one similarity class in which we are, in which T is an element, and you want to know the I keep on saying eigenvalue, characteristic root, characteristic vectors of T, then actually it's the same as asking what those things are for any other operators. Say this is T1 and this is T2. Now, for some reason, suppose that finding the characteristic roots and characteristic vectors for T2 is easier than finding those same things for T1. So within the similarity class, we want to find that element for which this is going to be the easiest. Okay, so that's what we want. So how can we do that? But before we answer that question, some simplification has already happened here. How? I mean, that's why we mentioned this fact. You see, now here's the thing. If instead of doing this job straight away for our actual t, we do the job for each ti separately, then obviously combining those ti's, you can create t. And you do understand what I mean by saying combining those ti's, right? What is basically what is t? T is a function, no? T is a function from V into V. And V is a direct sum of these subspaces. Now, say you have done the job for each Ti. What is Ti? Ti is something like this. And on Vi, T is actually just Ti. If you restrict T on Vi, that is what Ti is. So if you have done the job for each Ti, obviously you are going to know what T is and what the characteristic roots and characteristic vectors of T are. If you combine all the characteristic roots and corresponding characteristic vectors for Ti. Okay. So that is why the job of finding a suitable element in the similarity class of T has been reduced, has been simplified to finding that same thing for these Ti's. What is so simple about these Ti's? Can we not do it for T in general? I mean, we can try, but the good thing about these Ti's is the simplicity of their minimal polynomial. You see, the minimal polynomial of T is Px, which looks somewhat complicated like this. When you factorize, it's a product of powers of irreducible polynomials. But the minimal polynomial for T1, say, is only this. So naturally T1 is simpler than the general T. That is why the author says, because of this entire thing, it's, let me put it simply, in simple language, it's enough to do it for each Ti or simply for Ti. And what does that mean? It's enough to find a suitable element. I'm going to put this within quotes, okay? We need to make it clear what suitable element even means. But we understand that it's enough to find a suitable element in the similarity class of those operators whose minimal polynomials are somewhat special. Are powers of irreducible polynomials. That is, those minimal polynomials look like this. It's like trying to do something for say 12. I'm just having a little discussion which is number theoretic in nature. Say you want to do something for 12, something about this number, and you have found that it's easier to do it for 2 square and 3 separately. So obviously then the job gets reduced to doing that thing for this prime power and this prime, it's also a prime power. The situation is somewhat like that. Okay, so we can now afford to focus only on those operators whose minimal polynomials look like this. They are powers of some irreducible polynomials. And okay, now what does suitable element even mean? Exactly what are we trying to find in a similarity class? And we are saying, we keep on saying that we want a simple representative of that class. Simple in what sense? Simple in the sense that just by looking at the operator, you can say what its characteristic roots, characteristic vectors are. It will be very simple to find those things. However, it is still somewhat vague. Looking at the operator means what? Actually, that means looking at its matrix. So what we are really trying to say is this. You recall that in the third section of this chapter, where we studied matrices, we came across a result which is, what was it? I think Theorem 632, which essentially says this, that say you have an operator T on a finite dimensional vector space V, and there are two bases for V, say B1 and B2. Then the matrices of T with respect to B1 and B2 are similar. So whenever we try to do something computational related to an operator, say find its characteristic root, characteristic vectors, of course we use matrices. So the task of finding a suitable element ultimately gets reduced to the task of finding a suitable matrix or a simple matrix, which is as simple as possible, having say many zero entries, so that it's very easy to work with, like a diagonal matrix, if not a block diagonal matrix, something like that. So the question now becomes this. You have an operator like Ti whose minimal polynomial is a power of some irreducible polynomial, and you want to find a suitable basis for Vi, because Ti is an operator on Vi, a suitable basis for Vi in which the matrix of T, because if you change the basis, the matrix will change. The matrix of T in that basis has a very simple form. Can this be done? Yes, it can be done. And when you try to do this, you get Jordan canonical form. Now, this actually can be done for two different situations. The first situation is that one which we have already discussed today, which got us that corollary, in which all the characteristic roots of T lie in the underlying field. And that case we are going to see in this section. But there is the general case also in which that may not happen. Say some characteristic roots may lie in some extension of the underlying field. That general case we are going to discuss. I mean, in that case also, whatever we are saying we will do here can be done in that general case as well. That, however, we will discuss in the next section in rational canonical form. And to state what we are ultimately going to do finally in this section, we are going to need a definition. So let's see what this definition is. This definition is about a very special type of matrix. The matrix, the author says, but let me also emphasize that it's a square matrix. The matrix looks like this: lambda 1, 0, 0, 0, lambda 1, 0, 0, 0, lambda, and then a 1 will appear after that. And like that it goes. So there will be one row in this matrix which is the row before the last row. That will end like this, lambda 1. The entry before this is lambda, which I am not showing. But the very last row is this. So you have lambdas on the main diagonal, one on this diagonal which lies above the main diagonal, which is also called the super diagonal, and you have zeros elsewhere. Let me make it somewhat beautiful looking by using this ruler. Okay, so this matrix is it how we can write it whose main diagonal are lambdas? Or let me write it somewhat differently, where the lambdas are on, I don't have it written here exactly, so I forgot what the language is that the author has used. But the fact is just this: this is the matrix, this is the form of the matrix. Okay, so where the lambdas are on the main diagonal, which sometimes is also called the leading diagonal. The ones are on the super diagonal, and the zeros are the remaining entries, is called a basic Jordan block. Belonging to lambda. Okay, that's how we call it. Such a matrix is called a basic Jordan block. A basic because you can change the size of this matrix. It's up to you what size of a basic Jordan block you want to have. You can have a 1 by 1 Jordan block or 2 by 2 Jordan block, 3 by 3, any size you can choose. So that is why not the basic Jordan block, a basic Jordan block belonging to lambda. This lambda of course is going to change, and the other entries are 1, or 0 in this fashion. Okay. So now this is the final thing that we are eventually going to prove. Not today, but we will prove it in the next video. So this is what we are ultimately going to have. And in this theorem, we have that special case in which all the distinct characteristic roots of T lie in F. If T in AFV has all its distinct characteristic roots in F, say k of them are there, then V has a basis in which the matrix of T has the following form. It's a block diagonal matrix. And there are as many blocks as we have distinct characteristic roots. Where now we need to say what type of blocks these are. Where each diagonal block Ji is of the form which itself is also a block diagonal matrix. Bi1, this is a double suffix, okay. I represents the fact that it belongs to Ji, and 1 of course it counts the block, I mean which diagonal block it is. Bi2 Biri. This R itself depends on I because the size of it depends on J. How large, how small J will be, that I mean Ji will be, that depends on I. So we have Ri, not simply R. Okay. So this is already a block diagonal matrix, but each Ji itself is a block diagonal matrix, and where these things, these diagonal blocks are basic Jordan blocks belonging to the eigenvalue lambda I. All of them have this lambda I. in their on their diagonals, but the sizes may change. Okay, so that's why there may be many. May change means you may have said this is a 1 by 1 Jordan block, this is another 1 by 1 Jordan block. That thing may happen, but the sizes may change also. And finally, let us also see, because you see, we have seen the general form of a basic Jordan block. But let's see 2 or 3 examples so that it becomes clear what they actually look like, where we do not have this dot, 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 all these things. Now the simplest Jordan block, of course, basic Jordan block, has size 1 by 1, and it's just any 1 by 1 matrix. That itself is a Jordan block. So this is a 1 by 1 basic Jordan block. A 2 by 2 basic Jordan block is going to look like this. Okay, so you have lambdas on the main diagonal. Here super diagonal has only one entry, so that has 1, and the remaining entries, here there is only one, is 0. A 3 by 3 Jordan block, basic Jordan block, is going to look like this: lambda 1, 0, 0, lambda 1, 0, 0, lambda. So that's what I was saying when defining these things, that the row before the last row ends like this, lambda 1. Let's see a 4 by 4 also. So as the size increases, the definition becomes more clear. Lambdas on the main diagonal, 1s on the super diagonal, and 0s elsewhere. Lambdas on the main diagonal, 1s on the super diagonal, 0s elsewhere. Lambdas on the main diagonal. So as the size decreases, it becomes less and less clear, because you run out of room. But now you get the idea. So we are going to see the proof in the next video. And once it's over, the exercises will start, and then we will solve the exercises. So that's just it for tonight. Tomorrow we have again real analysis, where right now what are we seeing? We are going through the theory of integrability of monotonic functions. We have already seen that result. Okay, you know which one we saw recently. So we will see what comes after that. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.